Alright guys, so in this section 2.1, graphs of basic functions and symmetry, the first thing we want to take a look at is define if a function is continuous or not. Based on the definition, if you can draw the graph without lifting your pencil from the paper, your function is continuous. If you look at the function in the example A, you can see that I can draw my graph without lifting my pencil. This function is continuous. On the example B, it's obvious that it's discontinuous, and it's not, therefore it's not continuous. Well, we can say that it's continuous on a specific interval, and as you can see, from negative infinity to 1, by example, because of the open circle, we're having a parenthesis next to the 1, and always a parenthesis next to the infinity. On the interval negative infinity 1, we're having a continuous function. Okay, so we can also basically cut your function in different parts and define on this different interval that your function is continuous. When you look at the example C, you can see that I have from negative 4 to x equal 2 a continuous function, but at 2 I have an open circle. I can show you right there, you're having an open circle right there, and so therefore that means that you have a point that is not solution of your function. Therefore, you can say that from negative 4 to 2, you have a continuous function, and you have to use a parenthesis to show that 2 is presenting at 2 you are presenting a discontinuity. 2 is not a solution, so it has to be with a parenthesis. All right, so find the interval over which the graph is increasing, decreasing, and constant. I would like to remind you of a side how to prove that the function is constant, is increasing or decreasing. So for that, it's pretty simple. When you're looking at a line, and I'm going to take a very simple line, and we are on the Cartesian system coordinate, I can take 2 points on that line. Each of these points is defined by a coordinate x2, but also defined by a coordinate y2, which is the value of your function when x equals x2. I can completely do the same thing for a point x1, and I'm going to have, for this point x1, a value y1 equal at f when x equals x1. What I can see right here is that x1 is less than x2, and then I can also see that f of x1 is less than f of x2. And that helped me to define that my function is increasing. Now, if I look at another function, and let me draw the picture and then I get back to you. So as you can see in this second example, I still have 2 points, x1, f of x1, x2, f of x2. Remember this point right here as a coordinate x1, f of x1. y1 equal f of x1. And because we are on the y-axis equal f of x. And right here the x-axis. And I can see that when x1 is less than x2, this time f of x1 is greater than f of x2. And that means that your function is increasing. Okay? All right. So it is very simple also to define if a function is increasing or decreasing, especially when we are dealing with a line. When you're seeing a line going down, the slope is negative, you know that you are decreasing. So I can completely understand that from the interval 0, 1, I got a decreasing function. From the interval 1, 2, I got a increasing function. From the interval 3, 4, I got a decreasing function. But now, from the interval 2, 3, I can see right here that my function f of x, no matter which value of x I have, actually what I could write, it is very easy for me to basically say, when I look at f of x equal 2, it's exactly the same value than f of x equal 3, and that value is 3. And I can see that no matter which value of x, f does not change, meaning that you have a constant function. And so we say that during on the interval, let me use my 2, 3 bracket because I have solid dot, f of x is constant. Okay? All right. So in this course, the other thing that we want to look at is the symmetry. There's 3 types of symmetry: the x-axis of symmetry, the y-axis of symmetry, or the origin symmetry. And there is different ways to check this type of symmetry. Okay? The first test is to look at the graph. If by folding the graph along the x-axis, the 2 sides overlap, we say the graph has x-axis of symmetry. If by folding the graph along the y-axis, the 2 sides overlap, we say the graph has a y-axis of symmetry. And if by turning the graph upside down, the graph looks like exactly the same, we say the graph has origin symmetry. These are the graphing tests are easiest. They are the easiest one. But what we want to remember is very simple. To test for x-axis of symmetry, you need to replace y by negative y. And if the result is the same of the equation you started with, that means x is the axis of symmetry. Okay? So, what do we do is very simple. When I look at the example A, to check if the axis of symmetry, I'm going to substitute y by negative y. That gives me x squared plus negative y equal 9. Second step, I want to isolate y. When I isolate y, I end up to have negative y equal negative x squared plus 9. And when I have y by itself, I end up to have y equal minus negative x squared plus 9. Meaning basically that I end up to have y equal x squared minus 9. So when I compare with the original equation right there, and I have y equal negative x squared plus 9, I can clearly see that the original function y equal negative x squared plus 9 does not look like the same that y equal x squared minus 9. Therefore, I end up to say that x is not an axis of symmetry. Okay? Now, I can do exactly the same thing for y. To define if you have y as an axis of symmetry, I am going to first sub x by negative x. And so I end up to have, from the original equation, y equal negative x squared plus 9. And end up to have, at the end of the day, y equal negative x squared plus 9. Why? Because negative x squared give you x squared. And what can I say? I can see clearly that when I substitute x by negative x, I find exactly the same thing than the original expression. Okay? So therefore, I can definitely say that y is an axis of symmetry. Is an axis of symmetry. Okay? All right. If I decide to graph, I can clearly see that y is an axis of symmetry. If I fold regarding the axis y, I can clearly overlap. But if I fold over the x-axis, I can see it's not overlapping. So therefore, I can clearly say that yes, even graphically, I can see that y is an axis of symmetry and x is not. Okay? Okay, so let's focus on this example C. So on the example C, defining x as an axis of symmetry, you need to replace y by negative y. So I'm going to have negative y equal x plus 3, and up to have y equal negative x plus 3. Obviously, the new expression of y doesn't look like the original, so therefore, no, not an axis of symmetry. X is not an axis of symmetry. Okay? Okay, X is not an axis of symmetry. Now, if I do the same for Y axis, so this time I substitute X by negative X plus 3. I can clearly see that the new expression of Y doesn't look like the original. Okay, and so I can also say that Y is not an axis of symmetry. All right, so can I define O as an origin of symmetry? Well, right away I can see that line doesn't go through the origin, so right away I could say that it's not an axis of symmetry. O is not an origin symmetry. But if I replace x with negative x and y by negative y, I will end up with the same conclusion. So right now, y is not going, or the function, not y, and let's call the function, okay, the function f of x is not, or I'm not going to talk about the function, the line, because it's a line. The line is not going through the origin, so O is not origin symmetry. Okay, so you can see that on this graph. I'll let you look at all this interval of continuity and discontinuity. Very easy to find. Everything is on it is already written. Regarding the range of that function, let me write you the answers as I have only 2 more minutes to go. So the domain for the linear function is negative infinity to plus infinity, as well as the range. For the square function, the domain is negative infinity plus infinity, but from the range from 0 to plus infinity with a bracket for 0, because 0 is a solid dot. Now let's move on to the other domain, the cube and the square root, as well as the absolute value function. I'll let you do the cube f of x equal x cube, and you will show me that in class. Regarding the x-axis of symmetry, you will do the other problem by yourself, but if you want to know if x is the axis of symmetry, first you sub y by negative y, then you isolate y, and then you compare the original function with your new function y, and you end up for this one that it's not the same, so x is not the axis of symmetry if you compare the y with the original function. You do the same thing with the y-axis of symmetry. First you sub the x by negative x, then you substitute. So when you are at this point, you are going to compare the original function with the new expression of y, and you realize again for this function y equal x cubed plus 4x, when you substitute x by negative x, you don't end up to have exactly the same thing than originally, and so therefore y is not the axis of symmetry. It is the same idea for the making sure that O is the origin of symmetry. You sub x by negative x and y by negative y this time. And when you compare both at the end, you will end up to say that yes, you do have the same thing, and so you end up, as you can see, that at the end of the day, I end up to have y equal x cubed plus 4x, and so O is the origin of symmetry. So to define if a function is odd or even, substitute x by negative x, If you find exactly the same thing at the end, that means your function is even. That is the case for the example number